display our work, of course.
Okay, so I think we can start if everybody's ready. Welcome everybody to our Thursday colloquium. We have been, of course, doing this online since the beginning of the lockdown, and it's been almost 2 years now. And we've now moved to this format of having 2 a month Thursdays, and I'm glad to see that we still have a lot of our members and friends join us from time to time to this. We're very, very happy to welcome Professor Nicole Nesbadwa to our colloquium today. She's, as you can see from the beautiful picture up on there, is at one of the loveliest astronomy departments in the world, the Observatoire in Nice de la Côte d'Azur. And really, this is the view from the observatory. And
Argentina.
And then, so of course, she was a PhD student at MPI in Garching, and then has worked at various places in Observatoire de Paris, in Meudon and Orsay, and now she's at Nice. She's also been working quite a lot with various people at IUCAA, and recently with Dipanjan Mukherjee. She has now a new CEFIPRA Indo-French project that has been approved. So that also adds another dimension to this work. A lot of people here I know are interested in the subject, how AGN suppresses star formation feedback. And so I'd like to welcome Nicole to her talk. Up to you, Nicole.
Thank you very much, Mike, for the nice invitation. Thanks also to Dipanjan for having invited me. And yeah, it's a pleasure to be with you today, even though not physically and geographically, but at least virtually through Zoom. And I know how tired we all are of COVID and of the various travel restrictions that we have, and how much we feel all locked up for all this time. And so for once, I have chosen the view from our restaurant as the introductory slide, because maybe that all gives you hope that one day we can travel again. The 3 lines that you see in the center, I hope you can see the mouse, you can see the cursor. The 3 lines that you see here, by the way, they are part of our airport. That's the whole part here. And it's the 2nd largest airport in France after Paris. So it's easy to access. Yeah, next time I'll put up a slide again, because otherwise nobody believes that we can actually do work from here. The topic today I've chosen pretty large: how do AGN suppress star formation in galaxies? And the co-authors I have put up are some of the key people that I've been working with on the topic for the last 15 years or so. And I would like in particular to highlight, of course, Dipanjan, who's one of the core collaborators I have on that work in the last few years, together with Jeff Bicknell at ANU in Canberra and Alex Wagner at Tsukuba University in Tokyo. And as always, it's mainly the students who are doing all the work, of course. And I would like to highlight Marie Muller-Drevet, who's just started working with me here in Nice, but also, of course, Ankush and Meenakshi, who both are students of Dipanjan's, and who are doing important parts on the theoretical aspects of our common project. And then there's also Cédric Collet, who has been my graduate student when I was still in Paris a couple of years ago. Yeah, AGN feedback, I have been talking about this topic for 15 years, and for most of the time, we were never able to show actually what supermassive black holes, that there are supermassive black holes behind all of that at the center of the work. And I'm very happy that now for the last few years, we have been able to do that. And so let me just start with that by talking about the origin of AGN. So I don't know, many of you are certainly familiar with what AGN are. They're active galactic nuclei powered by supermassive black holes that are in the center, that are very massive objects that are like reuniting the mass of a small galaxy within the inner part of the solar system, essentially. And a few examples I can give you today is, for example, we know about the mostly inactive supermassive black hole that we have in our own Milky Way from the work of Gensel et al. And MPE, where we see that there is a big invisible mass thanks to the movement of stars that are orbiting around it. We also have the example of the Event Horizon telescope. That's a big millimeter interferometer that's combining telescopes all over the planet, where we have a very high resolution image of M87 that you see here in the radio with this fantastic ring structure and the central dark part. And one thing I would like to highlight in particular is very recent work of NGC 1068 that has been observed with an instrument we have built at the observatory together with collaborators, of course, that is now operating at the VLT of ISO in Chile, which is called Matisse, and which is one of the optical, or near-infrared, I should say, interferometers that are combining the light of the 4 telescopes, of the 4 UTs, into one single data set. And what you can see here is a very innermost part of NGC 1068, which is the nearest Seyfert-2 galaxy and an iconic object for AGN feedback studies. What you see is a very warm dust that you see in the mid-infrared between, say, 5 and 10 microns or so. On scales, on parsec scales, we have a resolution of 14 milliarc seconds. That is about 10 times, more than 10 times the resolution that you can get with the JWST at the same, and with MIRI at the same wavelengths. And it shows you the shadow of a torus, or maybe thick accretion disk that is the inner, in particular, this is what you see here through the lines. And on top of that, it shows you this bipolar structure that is probably coming from very hot dust illuminated by the accreting AGN that is being lifted off from the very inner regions. The paper just came out, and I'm not myself involved in this work, but I think it is really spectacular. And all 3 sources together give you a nice overview also of the different types of AGN, because most AGN are not active. Most supermassive black holes are not active in the galaxies. But then we have, of course, radio galaxies like M87, and we have, of course, also optically or bolometrically active radiatively accreting AGN like NGC 1068. So yeah, today we see them directly. But the main motivation for my work comes from very different scales. And what you're seeing here is a cosmological simulation. It's illustrious TNG, showing you the large scale filaments over many hundreds of megaparsec, and the dark matter that we know how it is collapsing under the influence of its own gravity, but we also know that it is mainly traced by baryons. Most of what we see, of course, comes from visible matter and baryonic matter, which is not only subject to gravity, but also to the 2 nuclear forces and the electromagnetic force, of course. And all of this makes the whole thing a mess, because we have all the complicated physics of gas heating and gas cooling, at the heart of which is also AGN feedback, because these models leave one big question open, which is, why is cosmic baryon cooling onto galaxies so inefficient? For example, when we look at galaxies, and when we count the baryon content in galaxy, we find that actually there's less baryons in galaxies than on average in the universe. We have the cosmic baryon fraction, the global cosmic baryon fraction that we can measure, of course, and within dark matter halos, the baryon content of galaxies is only about 20% of that value. So, and that's at best. So that's at the peak. What you see here on the plot is a stellar mass, is a ratio between stellar mass and dark matter halo mass as a function of dark matter halo mass. And you see that there is this peak at around 10 to the 12 solar masses with less baryonic mass, less stellar mass, at lower masses and at higher masses. At lower masses, we have a pretty good firm understanding that's probably mainly due to feedback from star formation. So stars form, they release energy, the energy is being deposited in the gas, drives outflows, outflows leave the galaxy, regulate, lower the star formation rate, either keep it constant at a low value or terminate it altogether. However, if we look at more massive galaxies, then this cannot be the case anymore because the dark matter potential becomes too deep. There's too much gravity for the gas to escape with star formation alone. So if we want to keep that gas removal idea alive, then we need a more powerful mechanism. And Silicon trees were the first in 1998 to come up with the idea that this could be due to AGN. And I want to highlight this plot in particular because I will come back to it at the end of my talk because we're having some very interesting results concerning that plot in particular. So this is one of the possibilities, since supermassive black holes are in the center of virtual galaxies. There have been studies by Sultan and by Johan Terrain, for example, seminar studies that have shown this. And because AGN can emit a large amount of energy in very short time scales, it's about the binding energy of a massive galaxy of few times 10 to 11 solar masses that can be emitted in a few tens of mega years. It seems very straightforward that the AGN may also be able to unbind the gas from the host galaxy that is there to form stars and do so pretty globally. There's just one big caveat in that, which is that we have to find a good way of coupling that AGN energy output to an energy input into the gas, and this is what most AGN feedback studies in the last 15 to 20 years have been working on essentially. There is a different possibility, which is that the dearth of baryonic mass in galaxies may also be due to a problem with gas cooling, and I will come to that in a little moment. Before, I would just like to talk a very little bit about outflows. This is not the main point of my talk today, but I want to provide a broader picture than just that basic idea of having star formation being limited because gas is outflowing, because the AGN is injecting energy into the gas. But winds are, of course, nonetheless pretty ubiquitous in galaxies. I'm showing just a few random examples here. They are not representative of the whole field because there's so many works today that have found evidence for outflows in all types of AGN that it's impossible to really summarize those. But just to give you a few examples, we do see outflows, for example, as in form of broad line profiles and absorption lines of H1. That's Raffaella Morganti's work in particular. Such features are particularly prominent in galaxies that have very young radio sources in this case. In our case, our line is not so nice that we have, but this is a very important galaxy because it's a galaxy where we only have a radio jet. We have no optically significant AGN. We have no star formation in this galaxy, and yet we have a depression of blue shifted gas over large velocity ranges. We also have evidence now. This is a galaxy without bright radio source, but just an AGN. We have evidence from long slits, of course, where we have these kind of bubble-like features, also at significant velocity offsets from the systemic velocity of the galaxy. This warm ionized gas in a nearby quasar. At high redshift, we have very, very broad. These are O3 lines with a little bit of H beta somewhere. Very broad, you see them here, very broad profiles showing us that there is outflows of a few thousand kilometers per second or so. This is again is warm ionized gas. We have molecular gas heated by shocks in galaxies where we also see neutral gas outflows in H1. For example, here with work with Spitzer that has been led by Pierre Guillard. We see the molecular world still in the millimeter, also broad outflows that we can probe in CO. This is work by Katie Alatalo on a nearby low power AGN. We have IFU data today, and just to give you another example of a iconic source where we see the disk component here, that's a large part, but then we see this little red and this little blue part here. And this is actually gas that is being lifted off by a radio jet as it is leaving the disk into which it is expanding, and it's dragging the gas along with it. Another example from Pierre Guillard, this time in absorption. And then we have also OH outflows, again, of molecular gas that have been seen by Herschel in absorption, for example, by Stéphane Mailloux et al., which can be either from AGN or star formation. So you see there's plenty of outflows. For me, the most magnificent example of mass outflows from galaxies, actually in galaxy clusters, I'm giving you here an example of a nearby very massive galaxy cluster that has been observed with Chandra and with VLA. And you see the brightest cluster galaxy in the center, and you see these magnificent radio halos where you also see how the radio emission is displacing the hot X-ray gas in the halo. It's creating these gigantic bubbles, showing us that outflows driven by AGN can heat the gas, displace the gas, affected out to megaparsec scales of megaparsec and cluster scales. So these are really the processes that are regulating baryon cooling on the larger scales where matter is gravitationally bound in the universe. There aren't that many works yet that are really unifying all those disparate observations into one common picture. But one example in particular for radiative AGN is work by Fiore et al. From 2017, where they took about 100 sources from the literature and they compared the scaling relationships of different wind tracers, be it molecular gas or ionized gas, broad absorption lines. Those are very dusty sources that have high velocity outflows that are fairly nuclear, or X-ray winds that are probing directly the regions very close to the accretion disk. And they did come up with a systematic evolution as a function of volumetric power of the AGN, giving prescription for mass outflow rates for the kinetic energy, and finding in particular that AGN are generally more powerful than in injecting energy than star formation if both processes are present. They find very short depletion times for the AGN of like 3 to about 30 times shorter than the depletion time from star formation. So it happens fast. Once the AGN is on, it's blowing out the gas very fast. And this may also be visible in lower gas fractions in the galaxies and others. However, in order to really remove the gas faster than it forms stars, it's best to be in a massive galaxy redshift less than 2. It's not clear at higher redshifts or at lower mass galaxies whether the effect is also going to be as effective than that. One interesting thing is that if you look at the curves of molecular winds for the mass outflow rates of molecular winds and of ionized winds, then it looks like there's progressively more gas being photoionized in the more powerful AGN, and there's a nice convergence with work that Meenakshi has actually put on AstroPH yesterday of her very first paper that finds a very similar thing for radio sources. Now that was about whether AGN outflows are important. I think they are in certain environments and perhaps not universally. The second possibility why there's not more baryons in galaxies is that there may be a problem with gas cooling. And I think, even though I'm certainly somebody who likes AGN feedback, this is also a very important point. There have been many different hypotheses raised that it may have to do with heating through cosmological accretion of gas as the gas is falling into clusters. The Virial shock may heat the gas. So may never end up in the galaxy. There is a possibility that morphological quenching, that means the steep gravitation potentials from spheroidal from stellar spheroidals may inhibit gas cooling in galaxies. High stellar mass surface densities can inhibit gas cooling and star formation, and there's other processes as well. So I think the question is still open whether we really understand the physics of star formation in galaxies well enough, and I think we have to also keep an eye open on those processes. Now we'll talk at the end, and we'll talk about that avenue. To talk more about morphologiquenching, which I think is one of the very interesting mechanisms, there has been work by Marie Martigues about 10 years ago who has been looking into this with SPA simulations. And there's also been very recent work by Gensio et al. In Heidelberg that I think is very interesting, because they do find an offset, what we call the Schmidt-Kennicat relationship, which means that there, for a given amount of gas mass that you see here on the left side of the slide, you see the gas mass surface density gas at a certain mass surface density. There is a close relationship with a star formation rate surface density, which we know empirically, and normally galaxies fall onto this sequence. Now, when they modeled galaxies with stellar disks and various bulge fractions, they found that as they went up to higher and higher mass bulge fractions, that gas cooling, that at the same gas mass surface densities, there was less star formation than you would find in galaxies, in disk galaxies. And this is very important because most studies of star formation have been done with disk galaxies. At the same time, another popular way now of quantifying star formation in galaxies is, or star formation efficiency in galaxies, is what we call the specific star formation rate. It's a star formation per unit stellar mass in a galaxy plotted against stellar mass. And this is also not a random relationship, but all galaxies, and most galaxies we know of that are actively star forming, seem to populate a certain sequence. If you have very short star formation timescales, and like starbursts, very ubiquitous star formations, you may fall above. And if you have no star formation in galaxies, you may fall below. But overall, you have that main sequence that you see here of star formation. And they also find that their bulge galaxies here fall below. And these galaxies have no AGN. So I think we have to control for these effects if we want to understand really what the unique impact is of AGN feedback. It's not enough to see that there's AGN with perhaps less star formation, but we also have to see, or with outflows, but we also have to see what are the mechanisms doing. And ultimately, we're also very used to thinking that AGN feedback works because we have developed a narrative over the last 2 decades where we always give the same arguments. If you're on telescope panels, you definitely encounter that. So we say that either it works because the energy injection is high enough to explain the galaxy mass function, particularly the offset between the black that you see here in the upper left, the black hole, the dark matter mass function, and the baryons. So there's fewer, at massive galaxies, there's fewer baryons per dark matter. We have also the narrative that we see a correlation between the black hole and bulge masses in galaxy, with the famous M-sigma relationship that you see here. We also see that they somehow co-evolve because the most luminous quasars are at the same cosmic epoch, about redshift 2 to 3, which you see down here, as the most vigorous star formation. And ultimately, we see all those wind signatures, and so they must work. However, for each of these arguments, alternatives have been proposed. For example, we have the gas cooling and dynamical processes for the mass function and the baryon deficit in massive galaxies, either through gas cooling or dynamical processes like gravitational heating or morphological quenching. The M-sigma relationship could also just be a consequence of self-similar dark matter assembly. And there's a very interesting paper by Mathieu and Janko from 2011 who found a pretty good correlation without any feedback mechanism at all. The coexistence of co-evolution of star formation and AGN activity could be due to fueling instead of feedback. And ultimately, it's not clear that whether even the most powerful outflows are always efficient enough in galaxies, in particular at higher redshift. And we should not ignore either that most AGN are not very, very powerful, and many galaxies have AGN and do not drive winds that are very strong. And ultimately, when we come to star formation, which is the ultimate goal of AGN feedback, we want to suppress star formation and baryon cooling in galaxies, at least instantaneously, we don't see much of an offset. For example, when Stanley et al. Compared the infrared luminosity from star formation with the infrared luminosity on the main sequence in bright optically selected quasars, they found that those quasars fall onto the main sequence over large redshift ranges. So it seems like there's no visible instantaneous effect, at least. And the same was found in star-forming AGN hosts, where the AGN are much less powerful, but also most galaxies have the same specific star formation rates as galaxies that are on the main sequence. So over large ranges of AGN, at least radiative AGN activity, there seems not to be a significant imminent effect on star formation. That can have many reasons. I'll be happy to talk about that later, why that is. But we have to show it. So we have to find a way of probing that there is a correlation, even if there may be ways to argument our way out of this. One of the big questions in AGN feedback is also, what is the main driver? Is it photons or is it particles? Is it what we call the radiative mode or what we call the radio mode? I don't like the word radiative and radio mode very well, but hence I'm saying photons and particles. We know that quasars are important. Quasar activity, radiative AGN activity happens while star formation is also happening. And we also know that most of these very bright optically selected quasars do not have strong radio emission. Only about 10% of them are cases where the radio emission is stronger than the bolometric emission. Those arguments together are still very seductive to many in the community to say that it's probably quenching from quasar, from radiative feedback, that is terminating starburst, either radiation pressure or gas heating through intense radiation of the nucleus. On the other hand, the radio, we also know that that AGN can accelerate particles to relativistic speed, which gives rise to synchrotron emission and is causing what we call the radio jets. And we found that these are in particular associated with low accretion rates onto the supermassive black holes that are like 10 to the minus 3 to 10 to the minus 5 or so of the maximal possible AGN accretion rate, which is the Eddington rate. And this means that there's a long-term energy release without significant black hole growth that is possible through the radio jets. We also know that all galaxies with stellar mass above 10 to the 11 solar masses have radio sources in their center. And so people think that instead of just quenching star forests, radio sources may maintain low gas contents over long timescales, and they've gotten used to dividing the world into these two areas. But it's actually also simple, because radio emission is also found in star-forming galaxies, and there's plenty of work showing that. And there's also plenty of work showing that outflows or strong gas perturbations in those galaxies are often associated with the radio emission and not necessarily with the quasar itself. I think one particularly important point is the number of radio sources that are found in massive galaxies, and we can really call them ubiquitous. I'm showing you here an example of the LOFAR telescope. LOFAR is a large radio megahertz array in Europe now that has a center in the Netherlands, which you see here, in the figure on top. But with antennae that are all across Europe, and actually even two that they're in Italy and Spain, with longest baselines of about 1,000 kilometers, which gives you a resolution of up to 0.3 arc seconds. And they're doing a large survey of the Northern Hemisphere currently. And one of the most interesting papers, I think, from that survey, look at the fraction of radio AGN as a function of stellar mass in galaxies from Sloan. They have, I don't know how many thousand galaxies now that they have been looking at. And they find that there is a progression. The higher you go in stellar mass, the higher the fraction of radio loud AGN above a certain low radio power. These are not very powerful sources, but they have noticeable emission, radio emission from an AGN. And you go up to 100% actually at a luminosity of 10 to the 11. At 10 to the 21 watts per hertz at 150 megahertz in the radio. We find the similar results found if you look at the fraction of radio AGN with a luminosity of at least the amounts that you see here on the x-axis in that range. So given that massive early type galaxies are key suspects for being sites of strong AGN feedback, I think this is a very strong argument that radio AGN are very important for that. One argument that has, I think, hindered the community a long time to fully acknowledge that is that when we look at the radio morphologies, radio jets are very, very narrow. You see here an iconic image on the left side from Cygnus A seen with the VLA, and you see this very narrow pencil-like morphology of the radio jet. However, this is in a way an observational bias, because we know that what we see in those fairly high, easy to do frequencies is in particular the very energetic synchrotron electrons that are also high surface brightness, and those are very young, and there is probably a large part of lower frequency, less energetic emission, lower surface brightness that is not seen in these images, given that GMRT is just around the corner for you. As I've just learned, I think you're probably aware of that. But I would like to show you also an example from LOFAR again, which puts this directly into perspective, because you see here in the little inset, you see the typical image of another iconic radio galaxy nearby, which is 3C3231 in a small group. And here you see the high surface brightness emission. But then when you go deeper and you look at lower frequencies, you see that this is only the tip of the iceberg, and that you have these very extended radio jets. And also, even though you don't see it very well here, also diffuse emission within those galaxies itself. So what we see in the radio is not everything. There's much more. Simulations show us the same thing today. So I'm just giving the Pangean simulation as an example, where you see, yes, you have the very energetic jet here with a very thin structure in the center, but you also see how much gas is being displaced and made turbulent, in particular, actually lower power sources rather than higher power sources. So again, the effects of radio jets are way beyond just the central part of the very high luminosity emission. And then if we compare the radio jets with the radiation from quasars, and there's another effect, which is that radio jets are energetic particles that radiate synchrotron photons. So the emission is not the primary mechanism that's putting energy into the gas, but it is only a tracer of it. And actually the mechanical luminosity can be a few hundred to even 1,000 times more than what we see in the luminosity of the radio. In the quasars and radiative mode, the situation is the opposite, because radiation itself drives the gas. There's several inefficiencies that, realistically speaking, in most galaxies, probably the kinetic energy is less than the radiation that we see, the luminosity. And as an effect, at the same numbers, at the same luminosity, a jet will carry much more kinetic energy than the radiation from an HGN. And I think this is also something that is not sufficiently appreciated in the product community. We can look at very powerful AGN at the energy and the momentum of the gas, and we compare that with the radio, with the kinetic power that we expect from the radio source. We have done that in a large systematic work of about 50, actually it's 49 galaxies at redshifts 2 to 3.5. So that's the cosmic noon, as we call it today, with the near-infrared imaging spectra of Symphony on the VLT. That was work I've done for about 10 years, actually. It was a big piece of work, where we see a whole plethora of phenomena. But what you see here as an example is one galaxy with very extended warm ionized gas that you see in O3, associated with radio emission that you see here as contours. You see that there's large velocity gradients. You see in particular very high full with half max. The gas is very stirred up, very turbulent probably, where it is affected by the radio source. Without going too much into details, we can extract kinetic energies in the gas from those galaxies, and we've done that here for the galaxies that is well resolved. And we found here the solid line is where the kinetic energy in the gas is the same as the mechanical energy we see from the radio jet. And then you have 10%, 1%, and 0.1% of the jet energy that's transferred into kinetic energy from the gas. And we see that we have that we can very well explain with pretty small energy transfer rates, transfer efficiencies. We can see that there is a significant impact on the galaxies, and we can explain those outflows with the powering by the radio jet alone, as opposed to other mechanisms. We've also checked against star formation and quasars that do not give enough energy and or momentum to explain the same thing. Simulations give us broadly the same numbers. I'm showing you here an example from Alex Wagner's work from 2012. It was kind of one of the precursors of the Pangean simulations today, who related full width of max of gas with jet power. And what I'm overplotting here are actually observed values. And we found for Eddington ratios, so that's for AGN activity levels, say, that are very close to the ones that he simulated, because we could measure them for the galaxies that are shown here as stars. We could measure them directly. We find a relationship between gas velocity and jet power that is very, very similar. So I think broadly we got the thing right. The question is now to look more at the details of the energy transport. How is the energy deposited in the gas, and what does that do to star formation? This works very well for high power sources. For low power sources, unfortunately, things get much more complicated because outflows don't work anymore in those. I would call them failed winds. We can also call them galactic fountains. Giving you here an example from work by Katie Alatello at low redshift and the galaxy NGC 1066. It's a beautiful study of a jet that is very low power, it's 10 to the 23 watt per hertz, we wouldn't see that at high redshift, for example. You see this very broad line in molecular gas and CO322. So the jet has an impact on the star formation. But when you look at the velocity offsets that you have, these are just like, I think, 150 kilometers or so between blue and red. And this is not enough to unbind the gas from the host galaxies. It's much less than the 5, 6, 800 kilometers per second we see in very powerful sources. The velocity here, watch out, that's heliocentric. That's not the relative velocities within the galaxy. We see a very similar situation at high redshift. Now this again work at redshift 2 to 3. That's been done by my graduate student Cédric Collet in Paris, where we look at the morphology of warm ionized gas, the velocity of the gas, again, which is much lower than in powerful sources, but the full width of max, the gas remains very turbulent. The full width of max stay very high. So there's no gas removal, but there is a significant impact of the radio jet on the gas in the host galaxy, which is significant. And I will talk about that more in a second. I'll skip that thing, I think. When we look at, so as a kind of summary of this first part, when we look at IGN-driven winds, we have plenty of observational constraints. We can look at the entrained material. We can look at the hot wind and the X-ray. That's a hot gas that is being directly accelerated by the outflow, or cocoon, and that's how we call it in the radio galaxy world. We have constraints on the very inner regions of the disk. We have constraints on the star formation that we can observe. So we can all put all of this together. And if we put this together, we have a scenario where we inject energy from either the radio jet or the quasar into the ISM of the galaxy, and then something happens with the ISM. It either is being accelerated as an outflow, so leading to gas removal, where we can calculate the kinetic energy and the cooling time directly from the line properties. And this thing will then suppress star formation because there's no gas left to fuel it. Or we can look at what happens to the gas that is being made to turbulence because clouds start to move relative to each other as shocks driven into the gas by either the hot wind or the radio jet plasma. And we can look at the impact that this has on star formation. And I think this is a channel of IGN feedback that is also appreciated in the community. And by putting all of the observables that I'm showing here in yellow, by putting all of them together, we can actually follow this process through observations and then compare with models and test the models on top of just using them for understanding what we do. If we talk about turbulence-driven star formation, we have to talk about star-forming regions, which are scales that are much smaller, of course, than what we observe normally in galaxies. That's a significant limitation. What I'm showing you here is in a region of Orion, seen with the HST. And if we go to even smaller regions, for example, as have been seen with Herschel and a number of star-forming regions, then we see that molecular clouds are highly structured objects down to scales of about 1/10 or so of a parsec, which is the width of these dense filaments of dust and gas that you see here. So nature is still not very, very well understood. But all of this hierarchy suggests very strongly that star formation is dominated by the effects of turbulence on the one side and magnetic fields on the other side, in particular very dense cores probably. And that these two processes together keep the star formation what we call inefficient. So out of the gas that is collapsing in one free fall time, only about 1% of this gas is actually forming stars in the end. This is a very rapidly evolving complex field in itself. But for us, there's one expression that is particularly important in the term in this context, which is what we call the virial parameter. It's something that we can observe also quite easily. It's just a relationship between the turbulent energy and the gravitational binding energy of the gas, which we can parameterize with certain observables like the line widths or the gas surface densities or the size of the clouds. There's lots of work. I just recommend a few papers here at the bottom that you can look at a starting point that describe this model in detail. We cannot access, we will never access 0.1 parsec scales in external galaxies, I think, at least not nice. But don't laugh, because we can talk about that later. Don't laugh. We are already at parsec scales in NGC 1068. So I'm getting a little bit hesitant about being too pessimistic here. But we have indirect ways of accessing these scales, because we can look at line properties. And what I'm showing you here is the emission of warm molecular gas as it has been observed with Spitzer, which is actually gas that has been heated by shocks. The dissipation length of shocks and galaxies is on the order of 0.1 parsec. So we do have some information about these scales. What I'm showing you here is a diagram that relates the warm molecular gas with the pH, with the brightness of the pH features, that small dust grains in the same clouds. And when we look at PDR models, so those are the outskirts of star-forming regions essentially, then we expect a certain ratio between these two components that are when they are being heated by UV photons from young stars. We can relate that to the 24 micron luminosity, which is a measure of the power of star formation and AGN energy, AGN radiation. Sorry. We find many galaxies today that are falling above that limit, actually, and that means there must be another heating mechanism that is heating the warm molecular gas. And we know the warm molecular gas can be heated very efficiently by shocks. So we have a measure of the energy dissipation on the scale of 0.1 parsec, roughly, in external galaxies, as imperfect as it is. But it tells us there's something going on, that there is kinetic energy being injected into the gas, and that this gas is cooling very rapidly, is dissipating this energy very rapidly. We have looked at that in much more detail in a few nearby radio galaxies to see what the link to star formation is. One thing that is very, very interesting is when we look at these galaxies, these are nearby radio galaxies, and we look at the Schmidt-Kennicott relationship again. So that's the mass surface density of star formation compared to the mass surface density of molecular gas, means how much locally, how much gas of a certain density locally is going to be turned into star formation in a certain amount of time. Then we find that these galaxies that also have very strong warm H2 emission actually fall systematically below the normal relationship for normal star-forming galaxies that you see here. We have offsets of a few, between 10 to 100 or so, for different ways of measuring molecular gas. I don't want to go into that level of detail here. We have looked at, in particular, one galaxy, 3C326N, in much more detail. For example, looking with Symphony at the morphology of the warm molecular gas, and I'm showing you here the morphology, the velocity, and the full width of max, which tells us it's a rotating disk, but it's a rotating disk with very large line widths in the molecular gas, up to 650 kilometers per second. That's not a normal star-forming galaxy. It's a 3 kiloparsec disk of warm dense gas, and this galaxy is not forming any stars as far as we can tell, because our upper limit is 0.07 solar masses per year. I think it pretty much qualifies as no star formation. Even though it has gas mass surface densities of a few hundred solar masses per year, that's comparable to your LIRC or even a low power U LIRC. These offsets are significant, and they show us that there's a lower star formation efficiency. Since we have no signatures of relevant AGN bolometric emission or relevant star formation, I think the culprit is a radio jet in this case, which does give us enough kinetic energy to explain this extra turbulence. We can push further with this because we can compare now with what people know about star formation, molecular clouds, and turbulence regulated star formation, molecular clouds. And one of the criteria for that is to look at what we call the Larson relationships. Those are expected relationships between turbulent velocity and the size of molecular clouds that have been well established for the Milky Way, which you see in the plot here at the right in form of these little dots. When you have this magical virial parameter of 1, which means the turbulent energy and the gravitational energy is equal, then you're on the red line, on that red dotted line. It's a bit above the galaxy's Milky Way because we have surface densities, mass surface densities that are a bit higher in our galaxy. And so for the Milky Way, that line would be a little bit lower than it is shown in the plot here. But it shows you that galaxies, that molecular clouds fall on this sequence, and that critical alpha virial parameter tells us something about that turbulence is almost, but not quite, inhibiting star formation in those galaxies. You end up with this 1% of star formation efficiency. Now, if we look at our galaxy, then for the size of the scales that we can resolve with Symphony, we see that we fall way above that alpha virial. That means the gas is way too turbulent to form stars. And we can extrapolate that in different ways down to the scales of molecular clouds. And if that is really dominated, if that velocity is really dominated by turbulence and scales down all the way to the size of molecular clouds, then we know why this galaxy is not forming stars. It's not forming stars because gas is too turbulent, it cannot collapse. Problem was with SINFI about 10 years ago, we had no way of pushing to the spatial resolution that we need. But now, and that's why I'm putting so much emphasis on this plot, now we do, because JWST has been launched, and we have a cycle 1 project on JWST that will allow us to do the same experiment at the diffraction limit of the JWST, which will bring us down to the size of slightly below 100 parsec. Where we can get into the realm of molecular clouds. We can add a data point here and see if the turbulence injected by the radio jet in this case is inhibiting star formation in gas that is dense enough, otherwise to give you enough star formation to be a LERC or a low power LERC. I think this is going to be, I'm really looking forward to this. So JWST has unfolded, so I'm getting more and more positive that this is going to work. Just run up with this galaxy. When we look at the larger scale, so we have been able to trace, then we do see that there are complex line profiles already. We see that there is a low power wind. The wind is lifting some of the gas off. It's up here actually. It's lifting some of the gas off the galaxy, but not to velocities that are enough for most of the gas to escape. And also, when we compare the time scales of the mass outflow from the wind, when we compare the dissipation time of the turbulent energy that we see in the broad line widths in the galaxy, and we compare all of this with the rotational time of the disk, then actually we should not see a rotational disk rotation at all, because either the turbulent energy should dissipate so fast that all of the gas would start forming stars, or it should be lifted off in the wind, and so it should be strongly disturbed. And so what we have proposed is that there's probably a cycle of a kind of fountain effect where the gas is being lifted off and falls back, which is probably one of the important drivers of turbulence in this galaxy. This is also something we will be able to revisit with JWST and say in much more detail. It's one example that we've studied in detail, but actually there's many more examples where we see broad warm molecular gas, this time in the near infrared gas that is much warmer than the gas we're mainly interested in, but still it's very close to our main gas phase of interest. I'm just showing you here an example from Henry Zavaro's thesis work at ANU, where you see again morphology, H2 velocity, and the full width half max, and we see pretty broad line widths all across the disk, even though the radio jet is actually much smaller than the extent of the disk. And what we have been hypothesizing is, again, that this comes from a component in radio emission that we cannot see. This is an example from dependence models, where we expect that we have this very small and compact, very high surface brightness emission in the center, but that's only the tip of the iceberg. And we have overall, we expect much more diffuse emission that we hope we can see, probably with SKA, and or maybe with deep low for observations. We will see. Maybe GMRT, and we could discuss about that. Now, as you see, I'm a firm believer that star formation is inhibited by radio jets in early type galaxies. However, we should not be too confident, and we should not generalize from one galaxy to the rest of the universe, of course. And we should also not forget that there are very serious efforts to find other mechanisms that would be more natural, because it would come out directly from the structural properties of the stars in the galaxies. All galaxies have stars, not all galaxies have radio jets. And so I want to go back to this morphologiquenching idea, because one of the things that you can complain about in the work I've just talked about is that we have been comparing early type galaxies like radio galaxies with late type galaxies like disk galaxies, which is where most work on star formation has been done. You see here again the Schmidt-Kenniger plot I've shown you before between star formation rate surface densities and gas mass surface densities, the normal galaxies, the galaxies with massive bulges in this work. And the question is a radio jet alone able to suppress star formation, or is this just a byproduct of something that's irrelevant to what's going on underneath, which is regulation of star formation through the bulge? So what we need for that is a disk galaxy, because mass surface densities are lower. The stellar structure is not bulge-like, it's not spheroidal, it's a disk-like in star-forming galaxies. And we need a spiral galaxy that has powerful radio jets. And those are very hard to come by, but luckily Jodie Bakchi had one of those galaxies. And I'm sure most of you probably know that source much better than I do. We just stumbled upon his paper from 2014 when we were looking for a galaxy to break the dichotomy between bulge stellar structure and presence of radio jets. And I was very happy to find that. And then we started following it up. And then after we had the paper almost finished, we contacted him, and he was so kind to join our work. And we've communicated about that. So it's pretty much now, and they're working together in expanding that approach quite significantly, actually. So what I'm showing you here is the stellar morphology as you can see it with the SDSS. Overplotted is the ALMA CO1 to 0 morphology, which shows a extended about, I think, 10, 11 kiloparsec large ring, which is avoiding. In the center, we have no emission. We just associated with biology has no emission. The molecular gas is associated with a disk. When we look at the velocities, we see the disk is rotating. Most of it is rotating very quiescently. We see very little deviations from the rotational motion. However, when we look at the line widths, we see that there is a significant enhancement in line widths at the regions that are associated with the inner radio structure, which you see here from first. We are having a VLA program in the queue to have better radio data. In the outer parts that are not affected by the radio, we see line widths that are very, very similar to those in other massive spiral galaxies. This is a very massive spiral galaxy, 3 times 10 to the 11th mass. It's not a typical spiral galaxy, but it has typical stellar mass surface densities and a disk like other spiral galaxies, and that's what's critical for us. The molecular gas outside of the regions affected by the star formation has very narrow line widths consistent with those found in other galaxies of the same stellar mass and same stellar mass surface densities. That are also spirals and have no radio jets. But in the center, this enhancement is highly significant. It's a factor of 3 or so, 4, or even more higher than what we see in the outskirts. And it's above what has been observed in any other of these galaxies that have no radio jets. Radio jets in this case are marvelous. They're very well developed. They're very large. The radio source is probably very old, a few hundred mega years or so, at least. We have been looking at the impact on star formation that this has. First, in a disk averaged manner, because our constraints on star formation weren't very good. And we find that, again, you have the same kind of Schmidt-Kennicott diagram between star formation rate surface density and molecular gas mass surface density, with the normal star-forming galaxies lying around the sequence here, a bit different samples from before. It's a more modern version of the same plot. And I'm showing you the galaxy here. This is what we would expect for our normal assumptions on the molecular gas mass as it is derived from CO. It's a huge issue how to do that. I don't want to go into the details here, but we have been controlling for the systematics of these effects. And this is, for the people of you who know much about molecular gas, this is the extreme value we expect for gas that would be optically thin. So that is the lowest gas mass surface density we can plausibly expect for this galaxy. And we see that we are still far, far off from the sequence of normal star-forming galaxies. So that means the star formation rate is about a factor 30 to 70 lower than in normal galaxies. We're currently doing a detailed follow-up study with VLT-MUSE to look at the stellar populations, to look at the warm ionized gas, to look at the gas heating mechanisms. We have also CHEMOS to look at the shocked gas. We have 14 hours of follow-up time obtained with ALMA at 0.3 arc-second resolution, which will allow us to relate the local gas properties with a local star formation in a very good way. We have the JVLA data coming up and also eMerlin to look at the radio morphology in more detail, put all of this together. And poor Marie, my graduate student who's just started, is doing all of this right now and learning a lot about how to analyze data of a very different nature at the same time, to push as far as we can into really probing the relationship between gas and star formation as a function of local energy deposition from the radio source. There's a very encouraging parallel activity that is led by Ankush and Dipanjan on testing the same thing with the same formalism, actually, with the hydrodynamic simulations that they are doing by adding a detailed prescription for turbulence regulated star formation into their model. So they're not just using Schmidt-Kennicott, they're also using, for example, the turbulent velocities, and I'm sure Ankush and Dipanjan can tell you much more about this, so I don't want to go too much into detail. But even in our first kind of like first test study, which was not optimized to do this kind of work, we already see a significant decrease between the star formation efficiency between the between the simulations here in gray that have no radio jets and simulations that have, and the part of the galaxies that are affected by the radio jet. And now we have to get the numbers right, and I think then we will have made significant headway into showing that really radio jet is an important agent in suppressing star formation galaxies. Now, this was on the instantaneous star formation. There is another aspect of this galaxy, which I find really fascinating. It's not only one galaxy, but I think it's a really fascinating galaxy. Sometimes it's worth looking at individual sources because it is very complementary to what we can do for samples. Now I'm coming back to the plot that I showed at the beginning, which is relating the star formation, the stellar mass, the fraction between stellar mass and dark matter halo mass as a function of dark matter halo mass. This galaxy here has a dark matter halo that is somewhere around here. And this is one of the central plots of AGN feedback, right? And how we justify AGN feedback. Since it's a stellar mass, it tells us something about the integrated star formation history over Hubble time. There's been a very interesting result lately by Lorenzo Posti, who's been a postdoc in Groningen with Filippo Fraternali, and then now in Strasbourg, at the University of Strasbourg, who has been looking at H1 rotation curves from massive spiral galaxies, which also have very good constraints on the stellar mass content. And he found that actually, unlike early type galaxies that are following this relationship here or that relationship here, it's essentially the same work from a different group, but the same relationship all over again. Spiral galaxies do not follow at high masses, do not follow this decline, but actually spiral galaxies continue to increase the baryon fraction in that up to the value that you would expect from the cosmological, from the cosmic average baryon fraction in the universe. So they get up to 100, up to almost 100% here in baryon fraction, which could mean that if AGN feedback is the main agent, that AGN feedback works in bulges predominantly, but not in spirals. It could also mean that, of course, a bulge is doing the difference, but not the spiral. Now, what is interesting is that these spiral galaxies, all of the baryons are in stars. They don't have very bright X-ray halos. It have some molecular gas, but it's not the dominant mass fraction. So really the stars are the dominant mass fraction. What's very interesting, of course, to compare that with our source, which is a spiral galaxy, a typical mass of spiral galaxies, with a sole exception that it has very powerful and large-scale radio jets telling us that it has a radio source that was on for a long time. And this is what we've been doing. So we've taken the plot from Lorenzo's work. We really copied his work there. This is again the expected theoretical distribution. This is what we see from spiral galaxy. What he saw, but what he saw in the spiral galaxies. And he's also done the same work now for early type galaxies, which you see form a large cloud, but broadly they follow the relationship that you expect from cosmology here at the very high masses. And if we look at the stellar mass, so we do the same thing that they measured in the spiral galaxies without radio jets, and we look at the stellar mass, the baryon fraction compared, it's a complicated, that axis is quite complicated. So it's the baryon fraction of the galaxy compared to the cosmic average baryon fraction in the universe. And if we overplot that galaxy with a stellar mass alone, we fall within the range of early type galaxies and reasonably close to the theoretical limit. We have, in other words, 2/3 less stellar mass than what we would expect from massive spiral galaxies without radio jets. Now you see that there's a second point. And the second point comes from including the X-ray halo, because this galaxy not only has bright radio jets, it also has a bright X-ray halo. It's not a normal spiral galaxy. The halo is here, that the galaxy is a small embedded thing here in that X-ray halo in the Chandra image of much larger scales. And when we include the baryonic mass that we have in the X-ray halo, we end up in the same part of the diagram as normal massive spiral galaxies, which to us means that the galaxy, this galaxy here, got its fair share. The halo of this galaxy, the dark matter halo of this galaxy, got its fair share in cosmic baryons from the universe. It's just that all of these baryons are still sitting in the halo because they're hot. They're also still sitting in the halo. They have not condensed down onto the galaxy to form stars. And this is exactly what you would expect from AGN feedback to work over a long time scale. I have no idea why this galaxy has a black hole in the center, why this black hole is driving bright radio jets. This is, of course, what Joydeep is mainly interested in, and he reminds us of that frequently. And he's right. This is another very important question. But for us, it's not that relevant in this context because we know it's there, and we only want to see what the effect is once it's there. And I think the effect is that we have 2/3 less star formation in this galaxy than we should have, even though we have enough baryons. And I think I've spent lots of time on this one galaxy, but I think it's important that to get this right. I think I'm also pretty much done with my time. So I had prepared a few slides on Dipanjan's favorite topic, I think, which is positive feedback, which is normal for a modeler. But I think we can either put that in the discussion session, or he can tell you about this perhaps at some point, or maybe I can, because with the CEFIPA grant, I should come to IUCA in the next 3 years when COVID will allow us to travel again. And so I hope I will be able to meet you all in person. To sum up, so I think the role of AGN feedback in galaxy evolution is far from being settled, and I hope I could raise a little bit of doubt into that story that we always tell, that we feel like we've solved it all. And I think we're very far from that. And actually, we're entering now the era where we have a good starting point, a good general description, and now we can really ask the important questions to understand how we can put it all together, and also to see where it works and where it doesn't. We can start addressing the relative role of radio jets and AGN radiation. I think both are important in their own context. The question is, where is that context? How do they interact? And is there anything missing for other processes, for example? We don't really understand yet how low power AGN regulates star formation. I hope I could convince you that turbulence may play a role in that, but even that, for those galaxies that we've been starting to study, this is still lots of work in progress. There's many aspects of this that are not answered. A very interesting question is, how does AGN feedback fit into the broader environment of the many mechanisms that contribute to regulating gas cooling in galaxies? What's the place of AGN feedback? In what kind of galaxies is it dominant? Or what circumstances is it dominant? Is it always dominant? Is it only in some cases dominant? I think these are also questions we have not really started to ask yet. And I think for all of this, a combination of detailed observations and hydrodynamic simulations of radio jets and other processes is really essential to make headway, to put our theoretical understanding into the context of the observational constraints, and to also probe not just the outcome, but also probe the assumptions that go into the hydro simulations, I think. So yeah, that's lots of work to be done, and thank you very much for listening.
Thank you very much, Nicole. That was fantastic talk, and I really we look forward to the various other things that you couldn't cover today, and certainly look forward to your coming to IUCA and in person. Wonderful. I mean, I hope there will be lots of questions. Please use the hand up option of in under reactions, and please ask your question. I hope Nicole can be here for a few more minutes. Do I see any hands up? Anybody has any questions or comments? Dipanjan, did you want to comment anything before we go up to the questions?
No, I'm fine. I've been chatting with Nicole for a while now, but I will echo Nicole's thing that it's a fantastic talk, Nicole. And I think Nicole has made a very good case of why we should also consider turbulence and not just the ejective phenomena of AGN feedback as one of the prime movers of star formation. I'll just let there's some hands up, so I'll just let the people ask the questions.
Naren, start off.
Okay, thank you for this fantastic talk. So I have one comment that recently AGNs has been detected in dwarf galaxies also, and that might be a nice place to look at, because these guys are gas rich and have low potential, and if it has the AGN jet has a lot of environmental effect, that should show up very easily. So that's my comment. I have a question regarding this 3C 326, where you have shown the velocity field and the FWHM map, right?
Yes.
So yeah, it seems that the velocity field is not that much disturbed. It looks fairly regular and nice rotation, but you have this high FWHM, right? And that is true for the disk galaxy as well. So I suspect that, could it be the deposition of energy is happening in more cascading way, that it is hitting the medium, or increasing the turbulence, but not in a like bulk way to disturb the large scale velocity. I mean, if you have any comment, yeah.
Yes, I think that is a very good point. Yes, and I think this is essentially what's happening. There are limitations to. I'll put that up again and that slide up again and oh, I think that was wrong. Okay, I don't know. I think you can still see it. I want to touch it. So as long as you can see the mouse, everything is good. Okay. Yes, I think there are observational limits that we also have to take into account, because the beam size that we had, the PSF, I should say, that we had in the case of Symphony was as good as we could get it, but it was not. It's a bit less than 1 arcsecond. I think it's 0.8 arcseconds or something, but it's not. It's not sampling the total size of the disk very well, and the signal to noise was good, but it was not good enough to probe faint additional non-circular components in the gas. So I think there's room for some outflows, but I don't think that it's going to be outflows that are really entraining large amounts of the gas in the disk. I think that we can already say. So that is one of the motivations actually to use JWST, because with JWST we will look at the same gas again at more than 10 times higher spatial resolution. We will reach a PSF of 0.06 arcseconds. That's so 60 milliarcseconds. That's the diffraction limit of the JWST in the short wavelengths. And we will also probe the molecular gas that is slightly colder than what we see here. That's about 100 K rather than 1,000 K than the gas, like the gas that we see here. And that is important because it's going to be the dominant mass component of more molecular gas in this galaxy, shock more molecular gas in this galaxy. And this is going to give us the best handle of seeing what really the mass component is of outflows versus turbulent gas. But I think, yes, turbulent, well, I'm using, actually, I hope there's not too many like star forming experts in the audience, because then I would be a bit ashamed of using the word turbulence, because ultimately we haven't even shown that the messed up motions in these galaxies are really turbulent in any physical meaning of the word. But I think it is very plausible that they are. I don't know whether turbulent cascade has been fully established in these galaxies. If it is, then even approximately, then all of the things I've been saying are valid. If not, I think then we have to take turbulence as a too idealized mechanism for real galaxies, and we have to see up to what level it really applies and can really explain what we're seeing. That's always like it is, right? We're always limited by the amount of data, or by the quality of the data we have. We're also limited by the quality of simulations, say the resolution or whatever of the simulations that we have, and then we can try to make the best out of that. And I think it's very encouraging what we can do today, but we should definitely not stop and consider this a done deal. I hope that answers your question.
Yeah. Thank you. And the inclination is not too high to incorporate. I mean, to worry about the rotational broadening, right?
We have line widths of up to 650 kilometers per second.
Okay.
And we have a total velocity gradient, so that's from the top to the bottom, of less than 500. So no. Okay. The turbulent, there may be a little bit of contribution of turbulent broadening in the center, but it's not the dominant. It's not the dominant effect.
Okay, thank you.
You would also expect in the full width of max, you would expect to have a broadening in the middle. You would expect to have a broadening at the center of the contours that are actually stellar component, not off center.
Yeah. So, thanks.
Thanks very much. Thank you. Kandu next. Kandu, your hand up.
Yes, Nicole. Let me just cut this call. Very interesting talk, and I like this approach of putting together so many observational details, because generally cosmologists are ignorant about either the physics or the observations, and they just take blindly this relationship of the Moster et al. That you showed. I had a question and a comment. The question was curious about this fact that the spiral, the disk galaxies you showed, that they do not actually obey this relationship, right? How firm is that, and how much is it? How much is it established?
You mean? Wait a second. You mean?
The stellar mass, something.
That
was that Moster et al. Plot.
Oh, the Moster et al. Plot. Yeah, you should invite Lorenzo actually to give a talk. I'm just killing my. Okay, you should invite Lorenzo. I highly recommend it because he gives great talks. His work is robust. I mean, there are not very many galaxies that they have observed. It's maybe 15 or 20 or so, I think. But those very massive spirals, they are rare already, so it's a significant part, and they are extremely circumspect in the work they've been doing, way more than we are, actually, to be honest. I think the H1 measurements that they have on the dynamical masses are excellent.
Right.
The analysis they've done on the stellar mass is also very, very robust. So I think these results are robust. Understanding the reasons behind all this are, of course, still subject of further studies, but I think the basic result holds. They're also not the only ones anymore who find this. I've just seen another, I think it was a Chinese paper coming across AstroPH maybe a month or 2 months ago, where they tried something similar with the SDSS with more galaxies and not quite as nice data, but they confirm the result. It's also work by Patrick Adel in the US, who's extended the work to even larger galaxies or even more massive galaxies. Sorry, and he also finds very similar results. So yeah, no, this is a recent result. It's quite highly cited, but I don't think it's seen its full bloom yet of recognition. But I think it's work that is very difficult to refute.
Yeah, it's very interesting.
And I really recommend Lorenzo.
Okay, we will take
great talks. It's wonderful.
Yes. The comment I had was, of course, I enjoyed the fact that you said turbulence and magnetic fields are important for star formation.
Yeah.
The other player in this game, which is not often recognized as such, are cosmic rays, because radio astronomers only see the electrons, but the protons could carry an equal amount of energy, which is they don't lose easily.
I agree.
And so right now they're being recognized as a major driver of winds, at least in galaxies, outflows.
I agree.
But they could also be playing a very important role in all these things. So that's another thing to keep in mind. Yeah.
I fully agree, and I think this is a very important mechanism that we should keep in mind when we look at low power AGN in particular, because I think it's going to have an impact there. Yeah. We're looking here at processes that require high energy injection rates, and I don't think cosmic rays can do that. You can also look at the H2 content and at the properties of the warm molecular hydrogen lines, and from those you can put upper limits on the cosmic ray heating.
Yes.
We've done that. We haven't done that in the best possible way, but we've kind of started doing that. There was a paper we had in 2010, actually, where I'm first author, and working with ISM experts like François Boulanger, who know way more about that kind of physics than I do. And we ruled out very important cosmic ray fluxes in the case of 3C326. In the case of Joy Deep Spiral, we aren't really there yet, but I would also think from the kinematic evidence we have that cosmic rays are not the best candidate in this case. In a general sense, however, yes, I think this will be an important contributor, in particular to long-term kind of feedback and low power.
Yes, I'm not only thinking of the momentum that they deposit, but also all the heating that they can do from streaming instabilities, but also just the pressure that they have. Yes. For example, in our galaxy ISM, they contribute equal amount of pressure to the interstellar medium. So, yeah, and also there is not very much explored about how much AGN can feed into the cosmic ray population. Yes. Mostly it's supernovae and star formation. Yeah, it's just another planet.
It's a very good comment. You're absolutely right. It's a very good comment. Yes.
Thanks a lot. Thank you very much.
Maybe we should discuss this more actually, because well, I'll contact you.
Thanks.
Or maybe we can talk when I hope I'll be able to come to Ayuka. So maybe we can talk then more about this, because I think this is a very interesting topic. I know very little about that, about cosmic rays actually, and I would like to learn more about that. So
Yeah, thank you.
thank you. Okay, thank you.
Thanks, Pratik. Go ahead. Pratik has his hand up.
Yeah.
Yeah. Hi, Pratik. I'm happy I put in that disclaimer about the turbulence and our definition of turbulence. Okay.
So yeah, I actually wanted to follow up on Lorenzo's sort of result, which I was not aware of this. So what does this mean? Does it mean that there is no CGM in this galaxy and everything is in stars, which is very, very odd? I thought that all galaxies have most of the baryons missing. So these almost look like they're baryonically close, and not only that, all the baryons are in stars. So it's an astounding result, I would say, correct. And how do we understand it?
I totally agree with you. It's a very interesting result, and as I said, you should let him defend this because he's doing a very good job in doing this. However, saying they have no baryons in the halo is of course not the same thing as saying they have no bright X-ray halos, right? I mean that's a difference. So I would not bet on them having zero baryons in the halo. I think they probably have some. The question is how much gas is left in the CGM compared to the very high masses that they have in stars in their disks and bulges. Actually, I don't know how much bulge.
Okay. So related.
The dominant baryon. What's different between those galaxies and I would say early type galaxies of the same mass is that the dominant, or as I say, cluster group central galaxies or something, to put it really to the extremes. The difference is that the gas in the halo is not the dominant baryon fraction, as opposed to some extreme examples of group central galaxies. So it's how much gas is where. And as I said, I wouldn't count on zero baryons in the halo. I think this is exaggerated, but much less baryons in the halo than in the stars, and with a ratio that is lower than in normal galaxies, and definitely lower than in 2345, where we have 2/3 of baryons in the halo, right? I mean, that's a very extreme ratio. And we should also keep in mind that these are pretty rare galaxies with an evolutionary history that's not entirely clear either. So for us, all of this is not so important because we're really just interested in as you know very well. I mean, we're really very, very interested in establishing that link between the energy deposition by the radio jet and the star formation and the gas, and that's in itself already quite a challenge. But the context of this galaxy and of the other galaxies that is massive biogalaxies is very interesting itself for many reasons.
Okay.
Thanks. It's an excellent question.
Thank you, Nicole.
Thanks very much. I don't see any more questions. I think I would then thank you again, and thank you for joining, Nicole. It's hard to applaud and express our gratitude over Zoom, but I hope we'll see you here soon.
I hope so too. And don't forget there's an airport.
Of course, I know.
As well.
No, I've actually been there. It's a lovely place, and I hope we can resume travel very soon.
I hope so too. Okay. No, thank you very much for inviting me. And have a good afternoon. Thank you.
You too.
Thanks, Nicole.
Thanks.